Sven, and he's going to present the paper on first choice maximal and first choice table, school choice mechanism.
Yes, so hello everyone, thanks for the introduction. This is joint work with Umut and Timo Mennle. Unfortunately, both of them can't be here today, so I'm filling in for them. This is a paper on school choice matching mechanisms, and we've studied these two very intuitive and popular properties and how they affect the design of these mechanisms. And I want to start with introducing you to these two properties. First, we cannot match every student to their first choice in school choice, and that's why we need some kind of school choice mechanism to decide who gets to go to which school. And maximizing the number of students who get their first choice seems like an intuitive and kind of desideratum and like a natural second best to everybody getting their first choice. And this number, how many students actually get their first choice, is often reported in the media. For example, here we have an article that says 45% of New York City 8th graders get into the top high school, so of their choice. Or here, also on the negative side, in England, 1 in 6 secondary pupils in England don't get into their first school. Okay, so this motivates this focus on first choices. And this is not only from the student side or from the media side, but also the school choice administrators themselves focus on this. So here we have an example from Denver's public school choice matching program, who are actually proud of how many students get into their mechanism, gets into their first choices. So they say 86, 80, or 87% of 6th or 9th graders were enrolled into their first choices, their reported first choices. And so this leads to the first desideratum and the definition we have in the paper, which we call first choice maximality, which requires that a mechanism matches a maximal number of the students to their reported first choices. Okay. So you can see first choice maximality as some kind of measure for the efficiency of the mechanism. In addition to efficiency, in school choice, we typically also want some kind of fairness requirement. And, oh, sorry, I jumped ahead. So the one mechanism that you probably all know and that satisfies first choice maximality is the Boston mechanism. So if you don't know it, here's a very quick recap of it. So the mechanism proceeds in rounds. In the first round, the students apply to the schools, and the schools accept the applications by some kind of priority order. So that may be by GPA, for example. Once a student is accepted, the matching is finalized, so already after the first round. All the students who didn't receive a seat at their first choice, then they apply to their second choice in the second round. And this process repeats either until all the students are matched to some school or until all the seats at all schools are filled. Okay. So Boston mechanism satisfies this desideratum of first choice maximality in an obvious way, but the Boston mechanism is not strategy proof, which is well known. So even though first choice maximality may be given on the reported first choices, it doesn't tell us much about what this actually means in terms of the true first choices. And this motivates the research question. In what sense, if any, does using a first choice maximal mechanism actually facilitate the matching of many true first choices, which we want as market designers, if we care about welfare? Okay, now we get to fairness, which I was already talking about a minute ago. So fairness in school choice is often formalized in terms of stability or no justified envy. If you have a student 1 that envies a student number 2, so you would like to be at the school that student number 2 got, then student 2 must have a higher priority at that school. So that is, then you don't have justified envy. And if the mechanism has that property, then the mechanism has stability. Stability, unfortunately, is incompatible with first choice maximality. This is independent of any kind of strategic considerations. And here's a simple but instructive example. So if you have 3 students, 1, 2, 3, that have these preference orders, A over B, and the student just wants into B or nothing, and we have 2 schools with 1 seat each that have the same priority order over the 3 students, then by first choice maximality, we need that to maximize the number of students that get their first choice, we need that student number 3 needs to go to school B but then either student 1 or student 2 will not get any seat, and because we can only put one student into school A, and then that student who doesn't get a seat will have justified envy towards student 3, because student 3 is ranked last by both of these schools. So given that we can't have stability if we want first choice maximality, we're going to relax this fairness concept, and we're going to define what we call first choice stability, which means that the students cannot have justified envy for their first choice. You can extend this kth choice stability concept in a natural way, but you can extend this example to show that any kth choice stability is incompatible with first choice maximality except for k equal 1. So this is kind of the strongest kth choice stability concept that is still compatible with first choice maximality. So given these two desiderata, we in this paper study the class of all mechanisms that satisfy first choice maximality, our efficiency desideratum, and first choice stability, our fairness desideratum. So this includes the Boston mechanism, but it is actually a much larger class of mechanisms. And we study them in the standard model. So the students have strict preferences over all schools, and the schools have strict and known priorities over the students, so we assume that the schools do not misreport their priorities. And here's an overview of our results. So the first result is a procedural characterization of these mechanisms, and we show which members are actually in this class. The second is an incentive analysis, so how manipulable are these mechanisms. Third, we perform an equilibrium analysis, first looking at what happens if all the students are strategic, and second, if some of the students are strategic and some are sincere. And third, we show that the Boston mechanism, even though it's only one member of this class, has kind of a unique elevated position in this class of mechanisms. And as I go through these results, I will keep pointing out some kind of some market design implications from the theoretical results. Okay. So let's start with the characteristics and the members of this class. So our first lemma is that a mechanism is first choice maximal and first choice stable if and only if it matches the same reported first choices as the Boston mechanism. So in other words, you can think of this as any mechanism that is first choice maximal and first choice stable essentially has to run the first round of the Boston mechanism, and then it's in some sense undefined what it does in the following rounds. And this has a nice implication because it enables some kind of quick identification of whether a mechanism is first choice maximal and first choice stable. You just have to compare whether the first round of the mechanism is equivalent to the Boston mechanism or not. And here's a list of a bunch of mechanisms that are used in practice. So this is the Boston mechanism that is often used in the US, for example, in Minneapolis, Seattle, Lee County, San Diego. Here we have the adaptive Boston mechanism, deferred acceptance, asymmetric Chinese parallel mechanisms, and TTC. So the adaptive Boston mechanism is more popular in Europe. It's a variation of the Boston mechanism where the students in the application process automatically skip exhausted schools. So if in the second round or third round they apply to a school, but that school already doesn't have seats left, the students will automatically go to the next school. And the asymmetric Chinese parallel mechanism is an interesting mechanism that kind of interleaves applications. You can think of it as interleaving applications of the Boston and the deferred acceptance mechanism, running some rounds and then finalizing the assignment, and then running a few more rounds of DA and then finalizing the assignment again. And the question is, after how many rounds do you finalize the assignment? And this is determined by this parameter E0. So if you finalize, the first time you finalize the assignment is after the first round, then this mechanism obviously in the first round is equivalent to the Boston mechanism, and then you also get first choice maximality and first choice stability. Okay. So now let's look at the incentives. The first result that's also easy to see but instructive is that no first choice maximal mechanism is strategy proof, even if we ignore first choice stability. Let's walk through this little example again. We have 3 students with the same preferences over schools, A over B, and the two schools again with this preference order, priority ranking over students. And now, because of feasibility, we only have two seats, one at each school. At least one of the three students has to be unmatched. So if they report their preferences truthfully, one of the students will be unmatched. So for that student, it will be optimal to misreport and rank B first, and that will be a beneficial misreport for that student. So in general, all first choice maximal and first choice stable mechanisms will not be strategy proof. But what does that tell us about incentives? So they are all in this class of not strategy proof mechanisms, but perhaps some still have better incentives than others by some kind of metric. And this is the question that this theorem answers. We have a method of comparing non-strategy proof mechanisms by their incentives due to Ithaca and Sven, who introduced this as manipulable as relationship. And our theorem says that if we have two mechanisms that are first choice maximal, first choice stable, and Pareto efficient, then these two mechanisms will be in that formal sense as manipulable as each other. So I find this quite surprising. For example, if you look at the Boston mechanism and the adaptive Boston mechanism, where the adaptive Boston mechanism in some sense does some strategic sophistication on behalf of the student, skipping over exhausted schools, they are both equally manipulable according to this incentive property. We have a second proposition which says that if you have a mechanism phi that is first choice maximal and first choice stable but not Pareto efficient, then you can create another mechanism psi that is Pareto efficient and also first choice maximal and first choice stable, that Pareto dominates phi, and where phi is at least as manipulable as psi. So here's a visualization of these two incentive results. If you have here the class of all first choice maximal mechanisms, here the class of all first choice stable mechanisms, and here the class of all Pareto efficient mechanisms. The first theorem said that within this set, all mechanisms are manipulable as at the same problems. And if you have a mechanism in this set that is not Pareto efficient, you can find one that dominates this one in terms of welfare and incentives. So here is a market design implication that I like. So for example, this means that the Boston mechanism dominates asymmetric Chinese parallel mechanisms in terms of welfare and incentives. So the question is, why would you use that in practice? If you care about just FCM, FCS, Pareto efficiency and incentives, Boston would be preferable to ACPM, but perhaps there are other reasons, some kind of interface reasons, some kind of cosmetic reasons that you believe are important. Okay, now let's look at equilibrium. So here we're interested in understanding the relationship between the Nash equilibrium outcomes and the stable matchings of the mechanism. And our theorem here says that for a fixed problem and a mechanism phi that is first choice maximal and first choice stable, a matching phi, a stable matching at the true preferences, a matching is stable if and only if there exists a Nash equilibrium where phi has this outcome mu. So the intuition is that the equilibrium outcomes of the mechanism correspond exactly to the stable matchings. This result generalizes a result from Ergin and Sven from 2006, where they proved this just for the Boston mechanism, and so this generalizes it to this larger class of FCM and FCS mechanisms. And so to give you a little more intuition for this result, essentially when all the students are strategic, the strategic students in equilibrium can grab their equilibrium school in the first round of the mechanism. And so then the equilibrium outcomes will thus correspond to the stable matchings. The formal challenge in the theorem is to show that this is actually enough to identify all the equilibrium outcomes. So what is the market design implication here? Because of this correspondence between the Nash equilibria and the stable matchings, if all the students are strategic, we cannot do better than deferred acceptance. So this kind of answers one of the motivating questions at the beginning of the talk. Is it actually useful to use these first choice maximal mechanisms? Well, so deferred acceptance implements the student optimal stable matchings in weakly dominant strategies. Here we have a weaker solution concept, just Nash equilibrium, not weakly dominant strategies. And we implement all possible stable matchings, not just the student optimal stable matching. So actually DA would dominate FCM mechanisms in two dimensions. And so this motivates looking at mixed settings. What if not all students are strategic, but some are sincere and some are strategic? So this was a point of view that Pathak and Sven took already in 2008. And for this setting, to analyze it, they defined what they call augmented stable matchings and augmented priorities. So to understand augmented priorities, this essentially means that a student receives a higher, so you take the original priority order and then you modify it to then allow an analysis of this mixed setting. And then you get that a student receives a higher priority at a school which she ranks higher in her reported preferences, and where strategic students get priorities as if they had ranked all schools first. So it's this new modified priority order. And then our theorem informally states that the Nash equilibrium outcomes of first choice maximal and first choice stable mechanisms coincide with these augmented stable matchings, up to equivalence for strategic students. So this partially generalizes the result from Pathak and Sven, who studied the Boston mechanism. Why this up to equivalence for strategic students? So recall that what we discussed so far, we said that first choice maximal and first choice stable mechanisms are defined essentially by the first round of the Boston mechanism, and the strategic students can grab, in equilibrium, they grab their equilibrium school in the first round of the mechanism. But it doesn't say anything what happens to what the mechanism does with the sincere students in the other rounds of the mechanism. And so this is what the theorem doesn't make any statement about. Okay. What we then also show is that the more sincere students you have in your setting, the more true first choices will be matched in equilibrium. So this is, I also find interesting from a market design point of view. So if the administrator actually cares about matching more true first choices, and if you believe that some students can be expected to be sincere in this setting, then FCM and FCS may actually improve the outcome. There's a caveat. Of course, this is only implemented in Nash equilibrium and not in weakly dominant strategies. So the solution concept is weaker than for deferred acceptance. Okay, so let me give you one more result and then I'll conclude. The final result is that the Boston mechanism takes this elevated position in this class of mechanisms that we discussed. For this, we define this additional property, which we call consistency. We don't call it, previous work called it this way, which requires that if you remove any student and her assigned seat from a problem, and then you apply the mechanism again, then the remaining students are matched to the same seats as before. And then to now prove what happens if you add consistency to the setting, you need some technical details. You need to also allow for zero capacity for the schools. And we need to extend first choice maximality to best choice maximality and best choice stability. And then our theorem says that the Boston mechanism is actually the only mechanism that satisfies consistency, best choice maximality, and best choice stability. Okay. With that, let me conclude. I've given you some results about this whole class of first choice maximal and first choice stable mechanisms, and I've shown that the Boston mechanism takes this elevated position within this class. If all students are strategic, we can't do better than DA, and in fact we do better due to the solution concept. If some students are sincere, then we can expect a larger share of first choices in equilibrium. We also have some idea for if you can expect some students that are sincere, you can now exploit this to design new mechanisms that actually work with the strategic students in the first round and then take the sincere students that are left in the second and further rounds and apply rank improving apply a rank improving mechanism to improve overall efficiency even further. Okay, thank you very much for your attention.
We have time for maybe one question by the next speaker from Satsa.
Yeah, sorry for going over time. Yes, Peter.
So you motivated first choice mechanism with the news stories. The journalists are obviously focusing on it because it's easy for them to understand and it conveys to the layperson some element of performance. But obviously it's a problematic measure of performance.
Yeah.
And I'm wondering if we should do a better job of explaining to journalists that it is limited and that there are better measures of performance, and perhaps giving journalists better measures of performance rather than focusing on first choice maximal as a worthy objective.
Yes, I think we should. So the paper, I think, makes two contributions, right? On the one hand, it shows that this focusing on this measure is short-sighted. Essentially, if all students are strategic, then you end up with something that is either equivalent to DA or worse according to certain measures. So then why not use DA that implements it in weakly dominant strategies and you get the student optimal matching? But it also acknowledges the fact that some journalists and some school choice administrators just focus on it so strongly. So we want to understand, well, what does it actually achieve in these settings? And so it's trying to make a two-pronged approach to this literature. I'm not saying that first choice maximality is the right measure. That's not what the paper is trying to do. Yeah.
Okay, let's take the speaker again.